Hello, welcome to my channel. Today we are discussing the questions from the topic electricity for Edexcel AS level physics examination. That too from the past 4 to 5 years of Edexcel board exam question paper. In fact, this is the fourth video of the series, and the link to the other three parts of the series is given in the description box. And these videos are good for even the other exam boards, since all exam boards include questions from the topic electricity. I shall show you how to answer these questions. Let's start with question number 25. So first 24 questions are answered in the other three parts. So please subscribe them and like and share my channel. So question number 25. There is a diagram with three identical resistors A, B and C. As you see, A and B are connected parallel, and this parallel combination is connected in series with the resistor C. The question here is, so we see that this is a loop. AB is a parallel loop. Now the question asked here is explain how the charge and energy, show that how the charge and energy both are conserved in the circuit, and with reference to the resistors A, B and C. So they are asking about the conservation of charge and energy. We know that current is the rate of flow of charge. So this is the definition we study for the current. Current is the rate of flow of dq over dt, the rate of flow of charge. Now in the circuit, there is a main current starting from the battery or the cell, let us call it as current I, the circuit current, and also let me name them as P and Q, the junction P and the junction Q. So the main current I, which is entering at junction P, is branched out, let us say as I1 and I2, because this is a parallel branch connection. So current I1 and I2 are entering into A and B respectively. Then at position Q or a junction Q, these two currents join together, I1 and I2 join together, and it flows as I, again as I, and ending up at the cell. So from the circuit we can write current from the cell is branched out and entering into the parallel resistors. So we can write I equals I1 plus I2. So at junction P, current I equals I1 plus I2. That means the current entering at junction P is equal to current leaving the junction P. Current entering at junction P equals current leaving junction P. Or we can say that because current is the rate of flow of charge, so we can say that as current is the rate of flow of charge. Current entering at junction P is equal to, or it is same as the amount of charge leaving the cell or the amount of charge given by the cell at P, the amount of charge given by cell equals the amount of charge entering R1, amount of charge entering R1 R1 plus amount of charge entering R2. So from this we can say that charge is conserved. So the amount of charge entering at junction P or amount of charge given by the cell is equal to amount of charge leaving the junction P or the amount of charge entering R1 and R2. So charge is conserved. So charge is conserved. So we showed that the total amount of charge leaving the battery or leaving the cell is equal to the total amount of charge given to the circuit. So the charge is conserved. Charge remains the same. Charge is conserved. Now about also, we studied a definition for voltage. Voltage is energy transferred by each coulomb of charge. Voltage is energy transferred by each coulomb of charge. And also since it is the loop of resistors A and B connected in series with the third resistor C, we can say that voltage given by the cell is distributed among the parallel loop. So we have a loop like we have two resistors, then this is connected to the next resistor C. This is C, this is A and B. So we can say this parallel loop of A and B is connected in series with the C. So from that we can say that the cell voltage is distributed among the three components in such a way that total voltage given by the cell, voltage of the cell, it is the sum of voltage drop across C plus the voltage drop across A or B, because A and B are parallel. So voltage at A is same as voltage at B and plus voltage at C. They added up and make the total cell voltage. So we can say that, or we know that voltage is the rate of energy transferred. So we can write as voltage is, or PD is the rate of energy transferred we can write energy transferred from the cell, that is voltage of the cell means it is giving an amount of energy transferred by the cell. Energy transferred from the cell energy transferred from the cell is equal to energy entering into the circuit. So from this we can say that, so energy is conserved. So total energy leaving the cell is equal to the total energy or the energy entering into the other circuit components, entering into the circuit or entering into the circuit components. So we can say that energy remains constant. So energy is conserved. Now let's move on to the next question. Calculate the total resistance of the circuit. Calculate the total resistance of the circuit, and the resistance of each resistor is 12.5 ohms. Total resistance. As we see, there is a parallel combination of two resistors A and B, and that combination is connected in series with C. So R total is resistance of A parallel to resistance of B, or A parallel B. To that, resistance of C is added up. And each resistor has a value of 12.5. So this comes as 12.5 ohms parallel to another 12.5, two resistors, 12.5 and 12.5, they are parallel, plus 12.5. Let us recall the equation for the total resistance when the resistors are connected parallel. Suppose we have two resistors connected parallel. Say we have two resistors connected parallel with the value R1 and R2. The equation for total resistance for that part is, total resistance is the sum of the reciprocals of the individual resistors. So R total is R1 plus R2. So instead of this, I can give you a short form to find out the value. Whenever there are two resistors connected parallel, if you do this way, after getting 1 over RT, then you have to flip it to find RT. So instead of that, at one shot we can find out the total resistance for a parallel combination of two resistors. It is just the ratio of the products R1 R2 over R1 plus R2. So this is the way we can calculate the RT value quickly. RT is product over the sum, the ratio of product and sum. So I'm going to use this rule here. So this is equal to 12.5 times 12.5 over the sum of 12.5 and 12.5 product over sum plus the series combination of another 12.5. So on calculation, this is giving me an answer of 6.25 plus 12.5. So there is a total resistance of R total. It's coming as 18.75 ohms. So this is the resistance, 18.75 ohms, total resistance of the circuit. Now let's move on to the next part of the question. The resistors are connected to a different cell with an EMF E as shown in the cell, and it has an internal resistance. Describe how a single ammeter can be used to determine the internal resistance of the cell. You should add to the diagram to show the position of this ammeter. Describe how an ammeter should be connected to determine the internal resistance. Internal resistance, that means we want to calculate the internal resistance R, and in this case they are telling that there is an internal resistance R also. Okay, So when you are connecting, and you have studied that we connect an ammeter in series to the circuit for measuring the circuit current. So we can say connect ammeter in series to the circuit. Measure the current. So let us connect an ammeter here to measure the circuit current, total circuit current. Then using that total current, so let it be I. So using that total current, we can calculate what is the total resistance. Total resistance of the circuit is EMF over the total current. They are using E as the symbol, E over I. This is the total current, but total resistance I mean. But we know that this total resistance is the external load resistor plus the internal resistance. So total resistance is R plus. So this R is the total resistance. I mean this R is the total resistance of this much. That is a loop AB parallel, and to that loop the series combination of C. This is the total resistance represented as R here plus this internal resistance R. So R plus R equals E over I. Therefore, from this we can calculate R equals E over I minus R. So this is the way we can calculate the internal resistance. Describe. There are no calculations, just describe how you connect the ammeter, and from the current reading, how do we calculate the value of R. So this is the way we can calculate the value of R. Let's move on to the next question. October 22. A student carries out an experiment to determine the EMF and internal resistance R of an electrical cell using a circuit containing an ammeter and a voltmeter. Draw a diagram of a circuit that can be used for this experiment. So we want to measure the EMF and the internal resistance. So we want to measure the EMF and the internal resistance. EMF E and the internal resistance R. So just now here we have seen that if you want to measure if you want to calculate the value of R, you have to measure the current. So we need an ammeter. Of course, we need a voltmeter, and also we need a variable resistor to change the resistance. So let us start with determine the EMF and internal resistance of an electric cell. So let it be a cell here. Then next to that, let us represent R as the internal resistance of that one. Then we need an ammeter to measure the current. Of course, we need a variable resistor, that is a load resistor, to vary the load and we can calculate. Then we need a voltmeter across that to measure the voltage at different values of current, load current. So this is the internal resistance, this is the cell voltage, this is the cell, an ammeter, voltmeter, and this is an the variable resistor. R is a variable resistor. Now the next part of the question is, the student plotted a graph of the internal potential difference of the cell against the current I in the cell as shown. Explain how the EMF and R of the cell can be determined from the graph. See here, EMF is the definition of EMF of a cell, that is the voltage of the cell when no current is taken. E, it is the voltage of the cell when no current is taken. This is the meaning of EMF of the cell. EMF is the voltage of the cell when no current is taken. That means I equals 0. So from this graph, wherever the I equals 0, so this is the position where I equals 0. So at that position, whatever is the voltage, that is the EMF. That means the intercept of the graph on the y-axis will give you the EMF. So it is a y-intercept. So we can write EMF equals y-intercept. Y-intercept of the graph or y-intercept of the line. That is when I is equal to 0. That is when I equals 0. And similarly, the gradient. The gradient of, this is a repeated question many times we have seen in the other videos also, you can see the gradient equals negative R. So R equals negative of the gradient. Whatever gradient you are getting, take the negative of that, that will give you the internal resistance. Now let's move on to the next question. A student set up the circuit shown with a cell with negligible internal resistance. The ammeter displays a current of 0.14 amperes. So it says that there is a current of 0.14 amperes. I equals the main circuit current. And there are 3 resistors, 9 ohms, 3 ohm and R. Calculate the value of the resistance of the resistor. Calculate the value of the resistance of the resistor. And it says that the EMF of the cell is 1.54. So it is says that EMF equals 1.54 volt. So we know what is the EMF and we know what is the current. So from that we can calculate what is the total resistance of this circuit. The total resistance of the circuit we can calculate. So let us calculate R total. R total is, again you see that 3 ohm and R are connected parallel, and that parallel combination is in series with 9. So R total is 9 plus the parallel combination of 3 parallel R. Okay. Now this is R total. This R total we can calculate using the current and the EMF. So resistance is EMF over or the voltage over current. I am using that formula. It is 1.54 over the current is 0.14. This will give an answer of 11 ohms. This is the total resistance. So I am going to write that 11 ohms here. 11 equals 9 plus. Now when two resistors are connected parallel, we have seen already in the previous two resistors R1 parallel R2. In this case RT, quickly we can calculate it as a ratio of the product and the sum R1 plus R2. So this rule I am going to use it here. It will be 3 times R over 3 plus R. 11 is 9 plus 3R. So from this, I'm transposing 9 to the other side. I'm getting an answer for 3R by 3 plus R, which is 11 minus 9. which is equal to 2, that is 3R by R plus 3 equals 2 ohms, 2 ohms, and from this, using the basic algebra, we can calculate the value of R. So it is, from here we can write 3R is 2R plus 3, therefore on calculation I'm getting a value of R as 6 ohms. I'm leaving the full calculation to you because it's a very basic algebraic calculation only. So we can calculate the total current, total resistance, but total resistance is a combination of 2 parallel resistors plus 9 ohm, and from that, using the basic algebra, we can calculate the total resistance. It is 6 ohms. Now, so 3R is, this will be 3 plus 2, this will be 6, not 3, it will be 6. Because on cross product 3R is 2R plus 6, okay, 2R plus 6, and therefore the total resistance will come as 6 ohms. Now let's move on to the next part of the question. The student made 9 ohm resistor using a thin copper wire with a diameter of 0.15 millimeter. Show that the cross-sectional area of the wire was about 2 into 10 to the power of, again the question is show that. Show that means you have to get this as the answer. This is not to be used in your calculation. You have to get this as the answer. Cross-sectional area, this is the answer you have to get. And it is given the resistance of the wire, then even the diameter it is given. So let us write the diameter. Diameter is 15 millimeter. Therefore, the radius is 7.5 millimeter, which is 7.5 times the prefix milli. The value of the prefix milli is 10 to the power of negative 3, this much amperes. This is the resistance value, the radius. Now we are going to calculate the area of cross section. So this is such a simple question it is. The area of cross section it is because it is a wire. For wires we are taking, we assume the wire as a cylinder, cylindrical in shape. So the base area is like a circle area. So area is pi r square. On calculation it is giving an answer of 7.5 minus 3 the whole square. Make use of your calculation. And it is giving an answer of 2 times 10 to the power of negative 8 meter square. Actually, it is giving a number of 1.77 10 to the power of minus 8 meter square, which is approximately 2. So we are getting the answer. Now let us move on to the next part of the question. Calculate the length of the copper wire used by the student. The resistivity of the copper wire is also given. The resistivity is also given. So it's already given the resistance, the resistivity we calculated. So we know the resistance, resistivity, and the area. The question is to calculate the length. How much is the length? This is what we have to calculate. Let us recall the equation connecting all of them. R is rho L over A, taking calculate the length of the copper wire. So taking L as the subject, it is R times A, R A over rho. So on calculation, on substitution and calculation, The resistance is 9, it is given in the first part, and the area we got it as 1.77 times 10 to the power of minus 8 over the resistivity is 1.68 times 10 to the power of negative 5, negative 8. It is given as negative 8 on calculation. This I'm leaving for you the calculation. So the length of the copper wire is a direct calculation only. That much meters. This is the answer. It is giving a length of the copper wire that much meters. Actually, you are getting the answer this as 9.48 meters. This is the answer you have to get. Now let's move on to the next part of the question. Calculate the drift velocity of the electrons in this copper wire, number of charge carriers per unit volume, the charge density. Charge density N is given. N is given, charge density. The current in the copper wire is given. Calculate the drift velocity. So let's recall the equation for or equation relating all of them. It is N Q drift velocity times A. So taking drift velocity as the subject, it is I over N, Q and A. On substitution, the current is 0.14 and number density is 8.49 times 10 to the power of 28 times the charge. Charge of the electron 1.6 into 10 to the power of minus 19 coulomb. This will be given. This information will be given in the data booklet. So charge. This Q means Q of the electron. Charge of the electron. 1.6 times 10 to the power of minus 19 times A. Area we already calculated previously. Area is 2 times 10 to the power of negative 8. We already calculated. So on calculation, the drift velocity, in fact, you have to use it as 1.7 only because your number is 1.7, not 2. Whatever you are getting, 1.77. This is not the one you have to use, okay? So on calculation, it is giving an answer of 5.8 times 10 to the power of negative 4 meter per second. This is the drift velocity of the electrons. 5.8 times 10 to the power of negative 4 meter per second. Now let's move on to the next question. It is 22 October. A red light emitting diode was placed into a circuit. Everything is given here, the voltage. The voltage is given, it is 12 volt. The LED emits light of wavelength 6.27. So this is a symbol for a light emitting diode. It is arrow shows that it is emitting light. So for this light emitting diode, it is emitting radiation of 6.27 nanometer. So lambda of the radiation is 627 nanometer. Then again for a prefix nano, the value is 6.627. Nano is 10 to the power of minus 9 meters. So this is the wavelength. It is 100% efficient. The battery has negligible internal resistance. So this is the EMF of the battery. It is given. When the switch is closed, the reading on the ammeter is 9.2 meters. So here the current is also given. The current milliammeter reading. So this is the current I equals 9.2 milliamperes. So the prefix milli is 9.2. Prefix milli stands for -3. The value of milli is -3. So 9.2 10 to the power of -3, that is the current. Now here the question is, so these are the informations given. The question is, show that the power of the LED was about 0.1 watts. This is the question. So here we have seen that the current passing through the LED, it is 9.2 times 10 to the power of -3, and the voltage, there is only one component connected, so whatever battery voltage that will appear across this LED. So the LED voltage is also 12. Therefore, the power dissipated by the LED, power of the LED, it is the voltage of the LED times power is current into voltage, current of the LED. Since they are in series, the voltage is 12 and the current is 9.2 times 10 to the power of -3. On calculation, it is giving an answer of 0.11 watts. So approximately 0.1 watts. This is the power dissipated by the LED, about 1.1 amps. Now the next part is calculate the number of photons emitted by the LED in 1 minute. Number of photons emitted. Here, one information about LED given is the lambda. Lambda, the wavelength of the light emitted, it is 627 times 10 to the power of -9. From this we can calculate what is the frequency of the wavelength emitted. This frequency of the wavelength emitted, we know that the wave equation for light, the product of wavelength for any wave, product of frequency and lambda is the speed of light or speed of the wave. So we are making use of that equation, and speed of light is 3 into 10 to the power of 8 over 627 times 10 to the power of -9. On calculation, we are getting an answer of 4.2 times 10 to the power of 14 hertz. This is the frequency of the light emitted, 4.78. So let me use that number here. So here we can write the frequency. The frequency of the photon. So here the frequency of the photon is, what is the number we got? We got the number as 4.2 10 to the power of 14. 4.2 into 10 to the power of 14 hertz. Here I have mentioned that frequency of the photon. See, we have studied in the wave, in the material, in particle nature, we studied that light is a wave, but light also has a dual nature. Electricity and waves, in the same unit we studied, light is, or the waves are having dual nature. Light is having dual nature. So light is made up of, as a wave it carries energy of the wave is spread all over the wave. But when you consider the the particle nature of waves, we assume that light wave is made up of tiny particles with a discrete amount of energy, and each particle we call it as a photon. So light consists of packets of energy. Light consists of packets of energy called photons. Packets of energy, photon. Photon is a packet of energy. Photon is a packet of energy. So for the light emitted by the LED, this photon energy we can calculate. For that, I know the frequency of the photon. Frequency of the photon emitted, it is 4.2. From this, we can calculate the energy of the photon emitted. Energy of photon emitted, which is Planck's constant times the frequency, which is Planck's constant is 6.63 10 to the power of negative 34 times the frequency. We calculated the frequency already, 4.2 10 to the power of 14. And on calculation, it is giving an energy of 3.17 times 10 to the power of minus 19 joules. This is the energy of the photons emitted. But now the question is, what is the number of photons emitted in 1 minute? Number of photons emitted in 1 minute. You can keep it as 1 minute, but we know that 1 minute is 60 seconds. So we have to calculate what is the number of photons emitted in 1 minute. So the total energy we already calculated the power of the LED, which is 0.1 watts. Then from this we can calculate what is the energy of the energy emitted by the LED. So I'm using that calculation here. So now I need energy of LED, energy of LED. What is the energy of the light emitted by the LED? This is its power into time, which is power we calculated 0.11 times 1 minute 30 seconds. So we are getting it as 6.6 joules. So this is the energy of the LED emitted. Energy emitted from the LED. It is 6.6 joules. Now what we need is the number of photons emitted. The number of photons emitted. See, here we have two informations. One is energy of one photon emitted, and the second one, this is the total energy of the LED emitted. Total energy of the LED emitted. So making use of these two, I don't have the place here, so I'm writing the next line somewhere here. I'm writing it here. The next sentence. Therefore, number of photons. Number of photons emitted, which is the total energy divided by energy of one photon. Energy of one photon, which is, what is the total energy? Total energy is 6.6 over energy of one photon is coming as 3.17. 3.17 times 10 to the power of minus 19, and this is giving an answer of total number of photons emitted per minute. It is 2.1. It is 2.1 into 10 to the power of 19. This is the total number of, so this is giving an answer of 2.1 into 10 to the power of minus 19, not minus, 19 photons. Sorry about that, there is no place. So I calculated the frequency, I calculated the energy of each photon emitted, then I calculated the energy of energy of light emitted by LED, which is 6.6 joule. So total energy over energy of one photon will give the number of photons. So here is the answer. Number of photons emitted, I'm getting an answer of 2.1 times 10 to the power of 19. This is the answer I'm getting. These many photons are emitted. Let's move on to the next part of the question. A red LED was replaced with a green LED which emits light with a shorter wavelength than the red LED. The current in the circuit did not change. Explain how the replacing LED affects the number of photons emitted in 1 minute. Explain how. So here we see that lambda of red LED was replaced with green LED which emits light with a shorter wavelength. Lambda photon emitted by red LED with a green LED which emits light with a shorter wavelength. Emitted for green, this is shorter than lambda of photon emitted by red LED. This is what is given as an information. Wavelength of green LED is less than the wavelength emitted by red LED, which emits light with a shorter wavelength than the red. Okay, so when lambda is less for green LED, so frequency of green LED, frequency of light emitted by green LED will be greater than the frequency emitted by red LED. Frequency of light emitted from red LED is less than, or frequency of light emitted by green LED is greater. And remember, this is we are going to calculate per minute. So it has a greater frequency. Therefore, photon energy, energy of photon energy for green is definitely greater than the energy of photon for red. Why? Because energy is proportional to the frequency. Energy is proportional to frequency. Therefore, when the frequency is higher, energy of the photon is higher. Therefore, the number of photons, but see, it says that the current in the circuit did not change. That means the power is not changing. The total energy emitted by the red LED is not changing. So so I'm writing total energy emitted remains the same. Total energy remains the same. So the number of photons emitted. So number of photons emitted per minute decreases. So green LED is the present one. So green LED, the photons have greater energy, but the total energy remains the same. Since they have more energy than the red LED light, number of photons emitted per minute decreases. Let's move on to the next part of the question. The maximum intensity of sunlight at the Earth's surface is about 1100. A student suggests that the intensity of the light at a distance from an LED with a power of 0.69 watts is greater than the intensity of sunlight at the Earth's surface. Assess whether the student suggestion is correct. So the maximum intensity of sunlight at the Earth's surface is about 1000. Okay. So the Earth's surface, the intensity, this is the intensity at the Earth's surface. Intensity of light at a distance 5 millimeter from an LED with a power of 0.69 watts. So let us see what is the intensity. Student suggested that intensity of light at a distance of 5 millimeter from an LED. So there is an LED here. Say it is an LED here at a distance of 5 millimeter. The distance the intensity falling here at this part, intensity. This intensity we are going to calculate, and we know that intensity equals power over area. And the power is already given. LED has a power of 0.69, so this is the power given. So power is 0.69 watts over the area. Area is suggests that intensity of light at a distance 0.5 millimeter from an LED. Distance 0.5 millimeter. So the area we will calculate with the equation 4 pi r square. Surface area 4 pi r square, which is on calculation. Here the distance 5 millimeter it is given, so that distance will come as a radius, because 4 pi r square surface area we are calculating. So this will be 0.69 over 4 pi into this is 5 millimeter, radius is or distance is 5 millimeter, which is 5 into 10 to the power of minus 3 meters, which is 5 times 10 to the power of minus 3 the whole square. And on calculating the altogether, it is giving an answer of 2196 per meter square. This is the intensity we are getting, intensity from the LED, intensity of LED, intensity of light falling from LED, intensity from LED, 2196. And which student suggested that the intensity of light is greater than the intensity of sunlight at the Earth's surface. So it's very obvious that this number is greater than 1100, which is greater than, so I'm continuing, which is great, this number, which is greater than 1100 meter per. Okay, so the student suggestion is correct. Student is right. Student is correct. Student suggestion is correct. Student is correct. Okay. Now let's move on to the next question. Equal lengths of two copper wires W, Z are connected in parallel in a circuit as shown. Z has twice the diameter of wire W. So it says that the diameter of Z. So here we have the diameter of wire, sorry, the diameter of wire Z, it's greater than the diameter of wire W. It has a twice the diameter, it says, so it is more, 2 times. Therefore, we can say that the area of Z, wire Z, is greater than the area of wire W. So from this we can say that the resistance of Z will be less than the resistance of W, as resistance is inversely proportional to area. Resistance is inversely proportional. This is area. This is area. This is resistance. R is resistance. So the resistance of Z is less than the resistance of wire W. Okay. Since the resistance of Z is less, we can say that the current through Z will be definitely more than the current through W because its resistance is less. But the question is, explain why the drift velocity of the charge carriers is the same. Drift velocity remains the same. So now let us think about the relation relating current. We reached up to current. Current is N Q velocity times A. This is the equation. Therefore, we have the drift velocity V is I over N, Q and A. But you can see that N and Q both are constants. That is V directly proportional to I over A, as N, Q are constants. Number of charge density and charge of the electron both are constants. So we reach till here. The drift velocity is depending on now I and A. Now let us go back to see the relation here. What is the order of, or what is the way, which way is the voltage, sorry, the area and the current are changing? Look at these two terms, the current term and the area. See, the current is increased, area is increased. Both are increased. So let us bring that concept here. So in this equation, when both current and A are increased, what is happening to the drift velocity? Drift velocity will remain the same only. Okay, so here I am writing, since um, both I and area increases, V will remain the same. So we reach till here. In this equation, both I and, since both I and A increases, V will remains the same. So both I and A are increasing at the same way. So from here we can write that is, so V remains same. So this is the answer we are getting. So we started from the diameter, then the area, resistance, current. We saw that current and area are changing the same manner. Current is more for Z, area also more for Z. Therefore, the drift velocity will remains the same. The change in area and change in the current are in the same manner. So, V will remains the same. Let's move on to the next part of the question. Now, these two wires are connected in series, W and Z. Now, the question is comparing. Complete the table by placing cross in the correct box for each quantity. We know only one thing. They are identical in length. They are identical in length, but their diameter is different. So we have the information diameter of W less than the diameter of Z. Diameter of Z. D is the diameter. Okay, diameter of Z is more. This is the only information we know. So previously we have seen that for both of them, here we have seen that for both of them, with the diameter, the area is more in Z than in W. Similarly, we see that resistance of Z is less in Z than W. So let me write that information also. So we have two informations here, diameter and the resistance. Resistance of W, is it W or Z? Resistance of RW is more. Resistance of W is more than the resistance of Z. These are the two informations. But whatever be the resistance, whether it is less or small, since these two connections are in series, the current remains the same. So, same value for current. What about the resistance? Definitely resistance for W is more. Since the resistance is more, the potential drop also, it will be more because potential drop is the product of V square over the potential difference, I into R. So resistance is same current, resistance is more, therefore potential drop is also more. Then the last one is drift velocity of the charge carriers in the wire. Previously we have seen the drift velocities, it remains the same because the wires were connected parallel. But here the drift velocity will be more in W than in X. Because we have the relation I equals NQ V area, or a drift velocity V is equal to I over NQ area. Okay, so current remains the same. So here we can say V is inversely proportional to the area, since I is the same current is flowing, N, Q are constants, like they are all the same. So we can say that V is depending only on area. V means the drift velocity. Now the area we have seen already the previous question, or the previous section, not the previous question, the previous section. The area is more for Z. Area is more for Z. So, and since they are constant, this is the relation we are getting. Also, we have area is more for Z than area of W. So, drift velocity of Z will be less than the drift velocity of W. So drift velocity of W is more. Drift velocity of W is more. So this is why I wrote a larger value in W. So explanation, this is the explanation. For this step, this is the explanation given. Explanation. Other two parts are easy, resistance and potential difference. So the potential difference, we are getting the potential difference V equals IR using that. Okay, let us move on to the next question. A student set up the circuit shown to investigate the properties of a negative temperature coefficient thermistor. The power supply has negligible internal resistance. Show that the voltmeter reading was about 6 volt. Ammeter reading is 23 milliamps. Show that the voltmeter reading. So the question is again show that the voltage is 6 and given the ammeter reading is okay. So the current is given as 23 milliamps, which is 23 times 10 to the power of minus 3 amps. So this is the current given. Then here you can see that there are two resistors that are connected parallel, and the voltmeter is connected across this parallel combination. So actually what we are calculating is the voltage of this parallel combination. The voltage of 500 ohm resistor will be equal to the voltage of the 600 ohm resistor, which is equal to the voltmeter reading. So for that, anyway, we know that the total current flowing through the circuit is, we have the value for the current. Current flowing through the parallel combination. So this is like a single piece. We can take it as a single piece. The current, the same current I is flowing through. I, that is the circuit current. The same current I is flowing through. So we have a voltmeter reading across 500 ohm is equal to voltmeter reading across 600 ohm as they are connected parallel. Okay, so now we can calculate what is the voltmeter or voltage of 500 ohm or voltage of 500 or a voltage of 600. So let me write this as the voltage of 500 ohm, and here it is the voltage of 600 ohm resistor. Voltage of 600 and voltage of 500. Okay, so we know the current and we know the resistance. If you know the resistance, we can calculate what is the voltmeter reading. So let us calculate what is the resistance of the two parallel loop. Resistance of loop. That means it is 500 parallel 600. They are connected parallel. This is the loop. So what I have written here, this is the loop. So 500 parallel 600. Let us use the easy way of calculating. It is the product over the sum, R1 plus R2. So I'm using that one. It is 500 times 600 over 500 plus 600. It is giving a total resistance of 272.72 ohms. This is the total resistance. Now with the total resistance of the loop, I know the current now, I know what is the total resistance. R total, I am writing R total of loop. So therefore, what is the voltage across the loop? The voltage of the loop, which is current into the total resistance of the loop. The current is 23 times 10 to the power of minus 3 times the resistance of the loop. Just now we calculated 272.72. So which is giving an answer of 6,272.72 into 10 to the power of minus 3, which is 6.227. So it is, I can write 6.3 volts, approximately 6 volt. So I have marked 500 and 600 in parallel as a loop. So voltage of 500 or voltage of 600 as they are connected parallel, which is the same as the voltmeter reading. So let me write that also. The voltmeter reading is 500 or 600 it is. So I'm calculating the total resistance of the loop. From that I'm calculating the voltage of the loop using Ohm's law. Now calculate the power dissipated in the thermistor. The next part of the question is the power dissipated in the thermistor. So we have another thermistor here in the circuit. So this is a thermistor given. We calculated just now what is the voltage dropped across the parallel combination or the loop. Therefore, the balance voltage is coming across the thermistor. So we have the thermistor voltage. Let us calculate the thermistor voltage now. V of the thermistor. V of the thermistor is the V of the cell or the battery. Is it a cell or the battery? It is given as a battery. So it is V of the battery minus V of the loop, voltage of the loop, which is 12 minus voltage of the loop, it is 6.3, which is giving a value of 5.7 volt. This is the voltage of the thermistor across the thermistor. Therefore, now the power dissipated by thermistor equals voltage times the current. The voltage is 5.7 and through the thermistor also the same current is flowing because it's connected in series 23 times 10 to the power of minus 3. So this is giving a value of 131.1 times 10 to the power of negative 3 watts. This is the power dissipated by the thermistor. So the next part of the question is the student decreases the temperature of the thermistor. Explain the effect of decreasing the temperature of the thermistor on the ammeter and the voltmeter reading. So here it says that the student decreases the temperature. So we can say as temperature decreases, it is a thermistor. So the resistance of the thermistor increases because we know that resistance of the thermistor is inversely proportional to the temperature. So this increases. When the resistance increases, the circuit current decreases. Now they want the effect on the ammeter and the voltmeter reading. So circuit current decreases, that is ammeter reading decreases. That is ammeter reading decreases. Okay. Now what is the effect on the voltmeter. So we reach till here, the circuit current decreases. When the circuit current decreases, the voltmeter reading V of the loop, or we can say the total voltage, it's not on the loop alone, the voltage drop across the load, that means the total resistance. This is decreasing, or in another way we can say thermistor on the ammeter and the voltmeter reading. So the voltmeter reading means this is the voltmeter. Okay. So the voltmeter reading also decreases. Let me write, it's the loop only. Next one. So as the current decreases, the voltage drop across the loop also decreases. As voltage of the loop equals current into resistance of the loop. So both the voltage and the voltmeter reading and ammeter reading both are decreasing. Now we will move on to the next question. A student set up the circuit to find out the internal resistance, EMF and the internal resistance of the cell. Current I is given. Okay, you can observe the circuit. Show that for this circuit R is E over I minus R. So the current flowing I, it makes a drop across the resistor. There is VR, which is I times R. And now also this current will make a drop across the small r resistor. It is I times R. Therefore, we can say that the EMF E is the sum of drop across R plus drop across small r. It is I R plus I times small r. I can say this is I times R plus R. So EMF equals I times R plus R. Therefore, from this we can calculate R plus R. R plus R is E over I. That is R equals E over I minus small r. This is what they want. Show that resistance is E over I minus R. So E is I R plus R. From that I am taking R plus R separately, which is E over I. Therefore R is transposing R to the other side. Now the next part of the question is, the student varied R and measured the corresponding value of I. The student then plotted a graph of R against 1 over I as shown. Determine the value of E and R for this. So here you can see that the gradient. The gradient is, so our graph is between R and 1 over I. So if when I am calculating the gradient, what I am getting is gradient equals R over, because delta Y over delta X, R over 1 over I, which is R times I. This is what the gradient I am getting. because we know that the gradient is delta y by delta x. This is the gradient. On the y-axis I have r. On the x-axis I have 1 over I. So gradient is, it's a product of I and r I'm getting. So this is nothing but it is the resistance. No, I'm getting some voltage as the gradient. So determine the value of E. Determine the value of E. So E equals gradient. Gradient which is equal to R over 1 over I, which is equal to R times I times R, which is a voltage. So the EMF, I'm getting it as the gradient. Now what about the internal resistance? Internal resistance is the y-intercept. You can see that there is a y-intercept coming here. So the internal resistance. Let us calculate the value also. Let us calculate the value also. So EMF is the gradient. So E equals, let us calculate the gradient, which is equal to, let us take the gradient from this point till here. So this is my delta y and this is my delta x. Therefore the gradient is 10 by gradient equals delta y by delta x, which is 10 over 8 minus 1.5, which is 6.5 volt. So this is the EMF I'm getting. EMF is 6.5 volt. So I have taken from this point. I'm just started here from this point. This is the gradient I'm doing. Okay, this is the gradient. This is delta x and this is delta y. So I got the EMF as 6.5 volt. Now what about the internal resistance? Internal resistance is the y-intercept. So I can write R equals the y-intercept. So actually R equals negative. I have R equals the negative of y-intercept, negative of negative 2, which is 2 ohms. So I am getting internal resistance as 2 ohms. So the y-intercept here it is negative 2. This is the y-intercept. I am getting it as negative 2. So internal resistance is 2 ohms. Now, the student suggested that the power dissipated by the internal resistance R decreases as capital R. That is, the load resistance increases, external resistance increases. Comment on the student's suggestion. The student suggested that, so we let us see, as R increases, definitely circuit current, I circuit decreases. Circuit current decreases. So, what is happening? So, the drop across internal resistance decreases. I times R decreases. This is what is happening. When the current is decreasing, the drop is also decreasing. So the drop is decreasing means the R value is decreasing. Therefore, the I square R is the drop across internal resistance IR decreases. That is therefore power I square R decreases. So power I square R decreases. So actually current decreases, therefore power I square R decreases. So this is the answer. The drop across the internal resistance decreases. Actually this is the answer. We need the power dissipation only. So power I square R decreases. Power dissipated by the internal resistor. That is power dissipation. Actually these are all happening because of the circuit current is decreasing. Power dissipation. R decreases. Current decreases, so R also, power dissipation decreases. Now the next part of the question is to make our time or to make our explanation easier. I have just copied the answer here. Already I have written the answer here. Let us see that. A student added a second identical cell in series with the first cell. Okay, he added a second identical cell in series with the first cell. So this we have to know when cells are connected parallel, in series, EMF total is the sum of the individual EMFs, E1 plus E2. So here it is, they are identical, therefore we are getting it as 2E, doubled. So doubled, the E value is doubled. Then, what about the internal resistance? Internal resistance is whether it is connected series or parallel, the internal resistance is also getting added up. Since it is identical, here also we are getting 2R. It is doubled. 2 times R doubled. So, from the previous question, okay, so we can say when second cell is added, what is happening to the EMF? EMF becomes 2 times the EMF of the previous value. Previously the EMF was 6.5. So 2 times 6.5. It was 1.5. 1.5. Let us check what is the answer for that one. The value was, this is 1.5. The number is 1.5. So this answer is 1.5. Answer is 1.5. So it is 3 volt. The EMF total now it is 3 volt. And what about the internal resistance? Internal resistance is 2 times. Previously the internal resistance was 2, so 2 times 2, 4 ohms. So now we need a graph of, the question is add a line to the graph. So we need a graph of internal resistance 4 ohms. That means the y-intercept should be 4. That is why it is coming here. So this is a new R new, total internal resistance. It is at 4. And we need a graph of EMF 3 volt. That means EMF 3 volt means the gradient has increased here. The gradient has increased means the line become more steeper. Since EMF doubled, line become steeper because EMF is the gradient. So the line become more steeper and its internal resistance is 4. And now we have to get the gradient as 3 volt. At the same time, the line become more steeper means the resistance is 10 ohms. The resistance is 10 ohms at a value half the value of the previous 1 over I. Earlier, the resistance become 10 ohm at a value of 8 amp per amp. So now this has to happen at a value half of the previous. So previously this it has reached a value of 10 ohm at this was happened at 6.5. Now it has to happen at a half rate. So here 1 over I must be half of 6.5 over 2. So that is 3.25. 3.25 per amp. That is why the new line, that is a red line, it is having an internal resistance or y-intercept of -4, and also it has to reach that resistance of R at a 1 over I value of 3.25. So from this point, let us count and see where is 3.25. So this is 1, 2, yes. So this is happening at this point. That is why the graph 10 is reaching here at a value of 3.25. This is 3.25. So this is the new line. Now let's see the last question. Calculate the internal resistance of the torch battery. For that, an EMF of 1.5 EMF is given. Then the terminal PD is given. Terminal PD is the total potential difference across all the load resistors, and the current is given. It is a very direct question. We know that E is equal to IR plus IR. This IR we call it as the terminal PD. This is a terminal PD plus I times R. So E is 1.5 and the terminal PD is 1.2 plus I times R. Therefore, we can transpose it. 0.3 equals I times R, and R equals 0.3 over the current is 280 milli stands for -3. So here this is 280 times 10 to the power of -3 amps. So this is the value of R, and that is we are getting an answer. R is 1.07 ohms. So this is the value of 1.07 ohms. This is the internal resistance. Now the last question, calculate the power transferred by the torch bulb. As we know, the power is the product of voltage and current. The current is 280 times 10 to the power of -3, and the voltage across the load resistor 1.2, because here the load is the bulb, torch bulb. So this gives an answer of 0.336 watts. So power is 0.336 watts. So this is the last question for this video. Thank you. Thank you so much.